evaluate the oxidation numbers and changes in the following equation. We're showing the hydrogen sulfide reacting with nitrate anion under acidic conditions to give you sulfur, nitrogen monoxide, and water. In the first case, we have hydrogen sulfide with sulfur having a -2 charge, and it's counterbalanced by hydrogen with a +1 charge, so that overall the molecule is neutral. Hydrogen has the same oxidation state as its charge on the cation, so it's +1. In nitrate, oxygen is -2. There's 3 oxygens, so you get -6. And overall, the molecule is -1, so the nitrogen has to be +5. Any element in its natural state will have an oxidation state of 0, as we see here for sulfur. Nitrogen monoxide, the oxygen is -2, so the nitrogen has to be +2 to give a neutral molecule. And in water, the oxygen is -2, so the hydrogen is +1. So we see that the oxygen remains unchanged. The oxygen is -2 here, and it remains -2. The hydrogen is unchanged. Both hydrogens are at +1 oxidation state, and it's still +1 in the water. Whereas sulfur starts out at -2, but then is oxidized to 0. Remember, loss of electrons is oxidation, so sulfur has lost those electrons and has a 0 oxidation state. Nitrogen is at +5, and it is reduced to +2. Gain of electrons is reduction. In the bonus question, we're asked to calculate how many grams of water would be produced by this redox reaction if you had 50 grams of hydrogen sulfide. So here we find how many moles of hydrogen sulfide there are by dividing by the molar mass of sulfur and twice the molar mass of hydrogen. We multiply by the stoichiometry. 4 moles of water is produced for every 3 moles of hydrogen sulfide, so that we find out that there's a 1.956 moles of water being produced. Then we multiply by the molar mass of water to find out how many grams of water. We're only allowed 2 significant figures, so we report our answer as 35 grams of water produced. In the second question, we're asked to balance this equation. So I separated it into half reactions. Here's the hydrogen peroxide turning into oxygen and the hydrogen ion, and we have dichlorine heptoxide turning into chloride. So the first step in balancing these equations is to make sure that you balance the oxygens using water. But in this case, you don't have to do that because the H2O2 turns into oxygen. So the oxygens are already balanced. You only have to worry about balancing hydrogen. So we're going to use 2 H pluses on the right, and then we balance the charges using electrons. So we add 2 electrons to balance off the 2 H pluses. So now there's no charges on both sides net. The dichlorine heptoxide forms 2 chlorides. And there are 4 oxygens here, 7 oxygens there, so you can add 3 waters to compensate, which produces an imbalance of 6 hydrogens. And the way you balance that off is by putting 6 hydrogens on the left. Then to balance the charges, there's a -2 net charge on the right, so to get a -2 net charge on the left, you add 8 electrons. Now that creates an imbalance in electrons, so this reaction is an oxidation that produces 2 electrons. This is a reduction that uses 8 electrons. So this reaction has to run 4 times before this reaction can get enough electrons to run once. That's why we multiply this whole reaction by 4. When we do that, we add the results, we get this, so 4 times H2O2, the Cl2O7, the 6H plus, the 8 electrons. So everything that's written on the left we put over here, everything that's written on the right we put over there. Don't forget to multiply all of this line by 4. Then what we do is we eliminate anything that appears on both sides. So we have H plus, 6H pluses on the left here and 6H pluses on the right. We're going to eliminate that and put 2H pluses on the right. Also forgot to eliminate the 8 electrons. Then we're asked to balance the reaction in basic solution. So because we first balanced it in acidic solution, to turn it into a reaction that's balanced in basic solution, what we do is add as many hydroxide ions as there are protons. So there are 2 protons left over on the right-hand side, so we're going to add 2 hydroxides. So if we do it on the right, we have to do it on the left, just like algebra. 2 H pluses plus 2 H minuses gives you 2 H2Os. You already have 3 H2Os there, so the total number of H2Os is 5. And when we rewrite the reaction balanced in basic solution, we have the 5H2Os written over there from adding these two together. These two obviously will have disappeared because they will have turned into water, and the hydroxide that's on the left is written on the left side. And then we write everything else to show it with the proper state. So this is aqueous, the Cl2O7 is aqueous, hydroxide is obviously aqueous, the O2 is gaseous, and so on. And that is the balanced equation. Now for number 3, we're asked to find the voltage that results from two half reactions. Now these are standard half reactions. You can look them up in any index in the back of a book or in the CRC. And when you calculate the total voltage of the cell, you add the reduction plus an oxidation, whatever the voltage is for those two respective half reactions, add them together to get the total voltage. So one of the reactions has to be an oxidation, and the other one has to be a reduction. You can't have two oxidations or two reductions, it wouldn't work. One has to take electrons, and the other one has to give them up, or one has to give them up, one has to take. So by definition, the hydrogen cell, standard hydrogen electrode, has a 0 voltage. The reduction of fluorine to fluoride is 2.78 volts. It's a favorable reaction. So the total voltage for the cell is 2.87. Then I added an extra question just to ready you for the final exam. What would the voltage be if the hydrogen ion concentration was 0.5 molar and the fluoride ion concentration was 0.6 molar? So I've made the product concentration lower than what you would have in the standard cell. So that, by Le Chatelier's principle, should allow the reaction to go more easily towards the right. And in fact, we see a slight increase in voltage when we use the Nernst equation. We did the reaction at 298, so we could use a simplified form of the Nernst equation. At 298, that's what you get. And you can use log Q because they've incorporated all the other variables that were written in here into one number. And N represents the number of electrons being exchanged. There are 2 electrons being exchanged here, so that number N is 2. We put in the concentrations involved. Don't forget that the stoichiometric coefficients become powers here. So whatever concentration of H plus is, raise it to the power of 2, because in the reaction, in the balanced reaction, you see there's a 2 next to the hydrogen ion concentration. So when we plug in all the numbers, it has a slight increase in the voltage. The fourth question, we were asked to combine 4 different reactions in all the different possible ways. There are 4 half reactions, each with their respective reduction potentials. And what I wanted you to do was to make every possible combination. So 1 with 2, 1 with 3, 1 with 4, 2 with 3, 2 with 4, and 3 with 4. Those are all the combinations you can have. Everything else would amount to a permutation. So if you had 4 with 3, that's the same as 3 with 4. So these are all the possible combinations. And let's look at the rationale for how I combine the voltages. In the first instance, we have 1 plus 2. And they're both written as reductions, and they're both negative. So how do you decide which one to flip? The first one has a higher negative potential. So if we flip both of them, because they both tend to go the other way, this one, the first one, will have a higher voltage. So that's the one that's going to go forward, and will drive that one backwards. And why does it have to drive this one backwards? Because you can't have 2 oxidations or 2 reductions. One of them has to be a reduction, the other one has to be an oxidation. So this is going to be the one that gets driven backwards because it has the lower voltage overall, the lower absolute voltage. So this one turns around and goes positive. This one has to continue going backwards because it has to be the one that takes the electrons, whereas this is the one that's going to be giving up the electrons as an oxidation. And the total potential will be 0.428. In the second one, 1 plus 3, still this one is going forward because it has the higher voltage of the 2. But actually, you don't have to reverse them because in this case, this one is reversed, and the electrons appear on the right for this one, the electrons appear on the left for that one, so that's perfect. And you get 2 positive potentials, the total voltage is 1.348. This is the reaction that has the highest voltage when it's coupled. 2 plus 4 gives you 0.858. Again, the first one was reversed. This one is left in the way that it's written. and so it subtracts from the voltage slightly. It's being driven backwards, so it sucks up some of the voltage from the first one. 2 and 3 are written so that number 2 is flipped, because it tends to run the other way anyway. And this one is plus 0.49 as written. So because they're both written as reductions, one of them has to be the oxidation. Which one is going to be the oxidation? That one. And it wants to run the other way anyway. So you get a total voltages of 0.92, because they're both positive in the way that they want to be. They want to run. So you get a reduction and an oxidation. And when you mix 2 and 4, you have to flip 2, and you leave 4 as is. So why do we flip 2? Because it wants to run the other way anyway, and so we need an electron on the right-hand side, since this one already has an electrons on the left-hand side. This one is the one that's going to be more positive when you flip it, so that's the one that ends up going forwards. This one will stay in the way that it's written. So the voltage on that, in that case, will be 0.29. And the last combination is 3 with 4. This one is a reduction. This one also written as a reduction, so let's make this one become the oxidation because it has the lower voltage. Well actually, it prefers to run the other way anyway, so 0.49, 0.14, both of them positive now, you get a voltage of 0.63. So the highest voltage you can get from all these different combinations is 1 plus 3, and the lowest will be 2 plus 4. We'll give you only 0.29 volts.